joining us on SPE TV. I'm Sarah Solomon, and there are a ton of benefits from being an SPE member. And I got a chance to catch up with attendees who tell me just how SPE has benefited their careers.
I've always enjoyed, interfacing, networking, meeting a lot of people, making friends, but also the technical content. You learned a lot from the various ATWs and OTC, etc., the papers at JPT. So it's just a great way of staying connected with the industry at large.
I've gotten to attend meetings which I find interesting and informative, and it might not be something that I normally see in my day-to-day work.
Make the most out of your membership by collaborating with other SPE members online, access papers and publications, and make a difference by volunteering.
And I've personally benefited greatly from it, benefited from volunteering to serve. I've served as session chairman. I've organized big-time conference for SPE, and it gave me a lot of opportunity to network and to also acquire some experience in leadership.
For one thing, the main manual I use in teaching my technical writing classes, because I use it as a style guide. And I've got to tell you, the list of petroleum engineering terms in that manual is priceless. Now, whatever I have to pay for that, worth it.
SPE is actually one of the major sources of technology. And whenever I need to look for something new technology or wanted to learn about something, I go to the SPE online and download these SPE papers.
To become a member, simply log on to SPE's website and click on the Join SPE tab. In minutes, you'll have access to member benefits. Memberships are good for 1 calendar year, running from January to December. So there you have it. Now, don't forget to renew your membership so you can stay connected to all the latest technologies SPE has to offer and the thousands of E&P professionals around the world. Thanks for joining us on SPE TV. I'm Sarah Solomon.
Hello, everyone. Good afternoon, good evening, wherever you are joining from. So that was just a short video on the importance of joining SPE. You're all welcome to the October lecture series brought to you by the Young Professionals and Students Liaison Committee's SPE Ghana section. This is the lecture 2 series of the mini insightful and educative session we had on Monday. In lecture 1, we spoke about the concepts, the principles, and the fundamentals of process control and instrumentation. In lecture 2, we are going to discuss about how we translate that theory into practicality. We'll look at the technologies involved, how it is being applied in the industry, and then the benefits that the industry derive from such operations. My name is Harrison Amwa, and I'm going to be your moderator for today. So this is just how our program will look like for today. From the house rules, SPE Safe Starts, you go to the main program and then to feedback, the upcoming events, and then the votes of thanks. Let's kindly take notes of some housekeeping rules. If you have joined, kindly mute your microphone. Also use the raised hand icon if you have any questions. And after the presentation, there'll be a Q&A session where people will start asking the presenter things that they didn't really get or things that they would want an answer to. So you can put those questions to the chat box. And if you have any contributions and suggestions as well, you can also put that in the chat box. SPE brings to you a safe start for safe driving in the rain. SPE recommends that you follow the necessary guidelines when driving. First, maintain a safe distance between vehicles. Stay in your lane and avoid overtaking. Drive at a slower speed than the posted limit. Avoid sudden braking. Avoid water overflown places and do not attempt to test it. By doing this, you contribute to driving safely on our various roads. Now we are going to have a very quick and interesting icebreaker session at this point, and I'm going to put a link in the chat box together with a game ID. So once you tap on the link, you'll be asked to enter your game ID. You copy the game ID and you paste it there, and then the game will start. So kindly check the chat box and then you find the link and the game ID there. Okay, so we have 5 people joining the game. When it gets to 10, we are going to start the game. Okay, we have 8 now, 2 more to go. 9, the last person, we are waiting for you. Okay, so the game can start now. Okay, so we've answered 5 questions now, 5 more to go. If you just joined, we are currently having an icebreaker session. And in this icebreaker session, we are playing a game. And in this game, they are being asked questions. And at the end of the day, we will choose, the game will automatically select our winners for us. So we have 6 questions answered, 4 more to go. Okay, 8 out of 10, 2 more to go. Okay, we are waiting for the last question. Okay, the game is over. Congratulations to each and every one of you. These are our winners for today. So we had a tie for the second position. So the second position goes to D and Ifwa. Congratulations to you. And our overall winner for Today's game is Officer. Congratulations to you, Officer. Thank you all so much for participating in this interesting game. We'll just dive quickly into the next session, and we would have Frimpong Kodia Sapon, the SPE Young Professional Chair, to give us an opening address.
All right, thank you very much, Harrison, and thank you all for making time to join the part 2 of this lecture series. Again, I'd want to say good afternoon, good evening, good morning, wherever you may be, and welcome all our distinguished young professionals and vibrant student community to this particular session. It's an honor to welcome you once again. This time is part 2 of the October lecture series. And as the theme suggests, is more focused on technologies, application, and industry benefits. When we gathered for part 1, I emphasized that our goal was not just to understand the concepts, but to ignite curiosity and inspire ourselves beyond whatever we know to shape the future of energy. We explored the foundations, the theories, the principles, and the science that makes process control, instrumentation, what instrumentation is, and what makes those two the language of precision in our industry. Today, we continue with that journey, but this time we are bringing those foundations to life. This session is where theory will meet reality, where what we studied on paper, theoretically, will find its rhythm in the field, in the control room, and across digital systems that keep industries running safely and efficiently. We're here to see process control and instrumentation in action, and also to understand not just the technologies and applications, but its real impact on the real world, performance, sustainability, and innovation. As young professionals, this is where our leadership will be tested. The industry is evolving. Automation, IIoT, and AI are redefining how we think, how we design, and how we operate. But beyond technology, it will take our generation's boldness, adaptability, and foresight to lead this transformation. Our collaboration with student liaison committee stands as proof that leadership is not just a title, it's a bridge. As YPs, we are supposed to provide direction, mentorship, and the young ones will bring in the energy, curiosity, and innovation. Together, we're creating a pipeline of competence, confidence, and continuity in the energy industry. So as we engage today, I encourage everyone to move from listening to leading wherever you find yourselves, from observing to contributing, and also making sure that your innovation doesn't stay hidden. The first session laid the groundwork, but today we're going to build the structure. Once again, thank you for joining and welcome to part 2 of this month's lecture series. And I'm sure your knowledge will grow beyond today. Thank you very much.
Coming right from Yao, let's turn our listening to leading. Thank you so much, Yao, for that opening address. This is the time that we all have been waiting for, and to introduce our speaker. He's in the person of Engineer James Asma, the Control Room Shift Supervisor at ENI Ghana and Exploration. Engineer James Asma has over 9 years experience in oil and gas operations, specializing in process control, plant optimization, troubleshooting, and quality management systems. With a background in chemical engineering, he has been actively involved in the construction and commissioning phases of process facilities, including instruments installation, loop checks, calibrations, and control loop tuning. His practical experience in integrating field instruments with control systems has contributed to improved plant reliability and operational performance. He leverages his expertise in computer programming and database management to develop digital tools that support data-driven monitoring, diagnostics, and optimization in industrial systems. Ladies and gentlemen, without further ado, let's welcome Engineer James Asma. Engineer, you can kindly unmute and proceed.
Hello, good evening, everybody. I don't know. I hope I can be heard clearly.
Yes, please, loud and clear.
All right, all right. Thank you very much for this opportunity, and thank you for the listeners as well. Since the introduction is already done, I think I'll just go straight into it, and um, I can share my screen, right?
Yes, please, you can.
All right.
Okay, the floor is yours now.
Okay, so I hope you can see my screen now.
Yes, please.
All right, that's perfect. So the topic for today is process control and instrumentation in action. So basically, we'll be looking at application of process control in the industries. So the areas we'll be looking at is a quick introduction into process control and instrumentation, and then we'll have a look at some few commonly used instrumentation in the industries, and then we'll delve into the control technologies, and then we look at some few case studies in the industries, and then have a look at the benefits, and then some few challenges, and then we end it with the future of process control and instrumentation. So we will start straight into it. So process control is basically regulation of process variables like temperature, pressure, flow rate, level to maintain a desired operating condition. For instance, I work in a gas industry, and we produce gas for power generation in Ghana. So there are set product specifications, or before the gas leaves the plant, there are some specifications that it has to meet. For instance, the temperature, pressure, and things, and even the composition, how much percentage of methane should be there, and how much percentage of nitrogen, and all those. So the customer will have all those ones set. So you have to meet those ones. So what process control does is to ensure that you're able to meet those product specifications, and as we send it to the customer. Now I am illustrating process control with this simple diagram here. So we have a tank, and then there's a sensor that is measuring the level in the tank, goes to a controller, and then it controls a valve here. Now, what you want to do, maybe the target could be, you want to keep it at 50% level. If the level start to drop, then the sensor will be sending to the controller that the target is, you are doing way lower than the target. So then you have to close this control valve here, which is the final element. You close it a little to build up the level back to the target. Or in the reverse is when it goes up, going higher than the set point. Also, we do the reverse. You have to open more and send more away so that you can keep within the target. There's always an operating envelope. So this is a level, but it applies to all other process parameters. So we have the operating envelope that you have to stay within. So that is what process control seeks to do. Now, instrumentation is the devices and the systems which we use to do that, to measure, to monitor, and to do the control. Some common, commonly used instrumentation, for instance, for flow, we have orifice plates, we have venturi meter, Coriolis mass flow meter, we have electromagnetic, ultrasonic, turbine flow meters. It depends on what you be measuring at the time, the product, and even cost and things. and the accuracy you need at a time at a point in time, or depending on the process, and you choose the flow or whichever transmitter you want to use. You also have pressure, gauge pressures, differential ones. You have absolute pressure transmitters. You have temperature transmitters also. Thermocouples, which are for wide range temperature reading. You have RTDs, resistance temperature detectors. Based on the resistance in the metal, for instance, usually platinum, and the resistance it has, there's a proportion with the temperature. So if it has higher resistance, then it will be reading higher temperatures. So, and then you have the infrared thermometers as well, and that is used usually when you don't have much access to the equipment. For instance, the running equipment is a rotating equipment moving around, and you want to get the temperature. You have something like a heat gun or sort of to get the temperature. So depending on the process and the accuracy, the cost, and all those things, then you choose, as well as the level and the analytical ones also. I try to show some of them here. The orifice flow. So the orifice plate is inserted in between the flanges, and then you read downstream and upstream of them the pressures to be able to measure the flow. And then you have these ones as well: temperature, transmitter, pressure, and then radar type, level transmitter, and you have stability, and so on and so forth. Now, the control technologies which are used, basically we have PLC, which is programmable logic controller. And that is basically a special computer that is being programmed for a particular function. So I think I showed something like this here. So it's something small like that, and then it is being programmed. So it can be programmed to start and stop a motor, a pump, for instance. Sometimes it can be programmed to time the sequence of a process. For instance, you may have a drying tower, maybe in two. It comes in pairs. So one will be doing the drying, the other will be in standby. So you can program the PLC so that if maybe 5 minutes for the drying sequence, and then it switches. So the PLC can be programmed for such things, and it can be programmed for even complex things, and it can be reprogrammed anytime. And then we have the DCS that has multiple controllers which have been distributed in the plant. So each one is doing a specific function, but they are communicating together. And then you have the operator station that can monitor, and then you can put any action, any control action from there. And then we also have the SCADA system. Yes, supervisory control and data acquisition. It's similar to the DCS, but the major area of concern is for monitoring. So for wide area monitoring, for instance, you need a SCADA, like let's say monitoring the water network over a wide area. You need SCADA. So the PLCs will be there in the field, and then it will be giving you the data on the monitoring system. So you can be far away, and then you still, by the network, you'll be able to assess and then to see whatever is happening at various areas. Even pipeline pressures, like what we do here, we produce into a pipeline network. Ghana Gas also produce into that, and it could be any other new company also inject into that. So you can use SCADA system to monitor over that wide range to check their pressures and the temperatures over time. All right, so usually the control loop is like this. This PT, pressure transmitter, that is installed on a vessel, be a tank or anything. Now it measures the pressure and then sends by electronically 4 to 20 milliamperes to the controller, and then you have a set point that the controller compares it to. For instance, if you want to keep it at, let's say, 100 bar, the PT or the pressure transmitter will keep measuring it, and when it gets to, let's say, it gets more than the 100 bar, it compares to it, and then the controller will send an output to the final element, which in this case is a valve, a control valve. There's a transducer which will convert the current to pressure, which will act on the valve, and then it will either open or close based on what you want. So in this case, if the pressure is going up, it will have to open the valve to let more out of the system to keep the pressure back to the target. And then when it's lower, is a reverse. We have controller operative modes. Usually, these are the standard ones that are there. You could set it in manual mode or you set it in automatic mode, and there's also cascade. Usually, especially when you are starting the plant, usually you want to put certain things in manual and then you switch it back to auto. Or in case you have an emergency, you can switch it to manual to fix something quick, and then you put it back to auto. So manual is where the operator himself sets the output, or is controlling the valve or controlling the final element by himself. And then the automatic is when the controller has set in to do the control. And cascade is when there's a higher controller. There's a controller whose output is now controlling a second or a slave or a secondary controller. So these are the modes that are there. It could be different for be named different for different vendors, but basically they are these. And then we have control strategies. The very common ones are feedback control, and then we also have feed-forward control. Feedback control is is where there is a deviation. I mean, when there's a deviation from the target, like the example I gave, if there's a deviation from the target, then the controller will kick in to bring it back to the set point or the target. Now, the feed forward is a little different. Now, in the feed forward, it wants to avoid any error. It wants to avoid any deviation from the set point. For instance, if in a pharmaceutical industry, maybe you're producing a drug, and then a little change in temperature can change can even make the drug ineffective or something. In that case, you wouldn't want to get the error first, and then the control will come in to solve it. Rather, immediately there's a disturbance in the system that would cause the deviation, then the feed forward is said that it has been modeled in such a way that the disturbance will be resolved before even to avoid having any deviation of that sort. So feed forward is usually used when you can actually measure the disturbance that can happen, and then you can model it to be able to avoid that. And then you also have some advanced ones like ratio control. You have cascade control, split range, and things. They are not the very common ones, but they are also used depending on the process. But the very common ones are these: the feed forward and the feedback. And then we also have PID control, they are usually termed as the algorithm or the control algorithms. So it's proportional, integral, and derivative control. It's used for it's actually with the feedback control. So when the error happens, when the deviation from the set point happens, then the PID control comes in. The proportional part and the integral part is the integral part is usually for accuracy. It tries to resolve the error in the system. And then they have the derivative part, which anticipates according to the rate, maybe immediately start to change, then the derivative part anticipates how far it can go, and then you try to resolve it even before the error reaches that high. So actually it can be used individually, like there are controllers who could only be proportional, and there are others which could have only proportional integral, and some have proportional integral and then the derivative. So depending on what you be controlling. Usually it is done at the engineering phase, and then to see if which one will be needed, or if there's a modification in the plant, you have to see to tune it again to see which ones will be needed at a point in time, and which percentages or how much you will need for each of them. It's actually mathematical calculations, and you have to usually in the system, so you key in the various values to tune it. These are examples of process control systems that we have, or DCS systems. And these vendors like Honeywell, Yokogawa, Emerson, and things, Siemens also, they are also into PLC manufacturing. So it's basically the same. So they run through SCADA PLCs as well as the DCS. The DCS is usually vendor specific, so it's a bit difficult to add other systems to it unless you get some specialized skill or maybe the vendor to help you in that. You look at some applications in the oil and gas. One of it is separator control, which I mean a separator that is applying level control to avoid maybe spillover or something. So this is a three-phase separator. We have water, which is the heaviest at the bottom. And then we have the condensate on top, and then we have the gas. Now, this can be made said that, let's say the level control on the left side could be set, let's say 30% to avoid water from spilling into the condensate chamber. So it said that if the level is going higher, then the valve at the water outlet will open to drain a little of it. And then you also don't want to go so low, said that you have oil coming into the water phase. So you place with it in that sense. So you put a set point in there, points are like 30% in that way. And then we have another level transmitter on the right side, which is for the condensate chamber. So it also keeps the liquid in there, so that you don't have doesn't go so high to have the condensate in the gas phase, as well as going so low to have the gas entering the condensate outlet. You could have a pump at the condensate side, and you wouldn't want to bring gas inside it, which can damage the pump. So that's one application of process control in this sense. Another application of it is in power plants. For instance, this is a gas turbine, and it merges or uses fuel, like fuel gas, for instance, and then mixes it with air ignite it, and then turns the turbine. Now, for instance, if there's especially in Ghana, when usually rain falls and you have power outages at areas, if there's a power outage like that, for instance, let's say we're doing 100 megawatts or something, and then the power goes down at some areas, the load would drop. Now, when the load drops, you have to adjust the fuel gas or the gas or the fuel that you are taking. You have to drop it also to keep the speed of the turbine constant. So in that case, you have the governor, which will be always calculating based on the load that is being served at a time. If the load increases, then it means that it will recalculate and then bring in to increase the gas flow into the system and the air as well. So that's this fuel gas air mixture control using the same process control approach to ensure that you have the turbine running all the time. Else, when there's any disturbance in the system, like a quick power shutdown or a quick increase, or maybe some huge equipment started, it will trip the whole system. But process control has a way to always adjust the components to be able to keep the system running almost all the time. Now, the benefit to the industries, one of it is improved product quality and then consistency. Improved product quality and consistency. Now, we said that the deviations from the target is one of the things that we check in process control. So once you're able to check that you don't have much deviations and things in the system, then you are ensuring that you are keeping some kind of consistency in your product. And then another benefit is that it's reduced operational cost. As you can see, it reduces a lot of man intervention in the system. So in that case, you reduce some cost in a way, and then you reduce the waste and things to you minimize your waste when your process control is functioning properly. So in that case, you end up reducing operational costs. We also have data-driven performance monitoring. For every industry, we have KPIs or key performance indicators. So based on the data that you have, because process control is able to keep an archive of all the readings on the various transmitters and things. So you can, at any point in time, you can have a summary of what you've done so far, how each of them is going, and the failure rate of a particular brand of transmitter. You can change it, so it gives you enough data to be able to do all this performance monitoring. And then we have reduced environmental impact as well. Like you said, that it reduces waste. In that sense, we reduce environmental impact. Like the example we gave, the case study we looked at fuel gas and then air mixture. So depending on the load, you wouldn't burn more fuel. If the load has come down, you reduce the fuel so that you don't burn more, releasing a lot of flue gases into the environment. Now, the challenges we have in process control, one of it is maintenance and calibration complexity. Now, you may have a big plant that has hundreds of transmitters, and to ensure their reliability, you have to be doing calibration for all of them over time. So you can actually do a preventive maintenance, you schedule to calibrate all of the transmitters in their specific times. So in that case, you need a lot of it's a lot of work actually, but it's a way to make the system reliable. And some of them to over time, after calibration, because it's been exposed to the environment, rain and things, you can have it swing away from the calibration point. So you need to do all those, and sometimes it can develop faults and things. So it becomes a bit challenge in there, and it gives a lot of work also. And then there is the integration of legacy and digital systems. Like old systems, maybe a DCS, a vendor has made his DCS, and now you have a modification, and then you want to add some other unit to it. It becomes maybe a bit difficult, especially if the programming languages are different. You need some skilled person to be able to uh, do the communication for these two systems to work. So if one is a modern system that you are bringing in and one is a very old one, there may be some few challenges with the communication. And then we have the cybersecurity vulnerabilities also, especially the fact that we are looking at um, the fact that now everything is becoming smart and things, you want to be able to view what's happening on your tablet or at a wider area, maybe in the headquarters or something. You want to be able to see what is happening. Because of that, it raises this cybersecurity concern also. And actually, there have been times that there have been instances that such systems have been hacked, and then the hacker will just start to change the set point of things. Maybe the pressure set point, maybe at 100 bar, the system will just rupture, and then he will just increase it to maybe 120 bar. By the time you realize some huge incident has happened. So that's one big incident. Usually they try to avoid uh, connecting the system to internet so that it has a local area network. And even that one, a pen drive that has a virus or some malware on top can can do something like that, can bring some vulnerabilities in the system. So usually the personnel are taught and then educated on some of these things, so that you don't click on some phishing mail links and things, to avoid some incidents like that. Now, the future outlook or the future of process control, one of it is smart sensors and IoT, that's Internet of Things. Now, some smart sensors, some of them can even, let's say, not only one parameter, you can measure pressure, temperature, flow, all at the same time. So you are looking at currently the plant I work in, we don't have that. But there are plants, the upcoming ones are looking at ones that can do all of them together, or some that can send you that you can view the reading on your phone, on your tablet, or at areas like that, wider areas. And then we also have AI and then machine learning. So the system will be moving into AI and machine learning areas where the system can be able to predict failures. Because now what we do is that there are field operators that may go around and take readings of certain transmitters, certain gauges and things over time, maybe an hourly reading or so. If a system is faulty and then there's a little spike here and there, you may not be able to capture that because maybe it didn't happen at the time you were looking at it. So in that case, it may be an issue. But once AI and machine learning set in, you'll be able to resolve some of these things because it keeps track of all this, and even in the microsecond, if the system start to fail, you'll be able to see according to the data that is being recorded, and then it can give you a prompt of it so that you either swap it, change it, or get a new one, or something like that. And then the cybersecurity integration. So as we uh, plan to have more smart sensors and things, then we have to heighten our cyber security as well. So it actually goes hand in hand. So in that case, you wouldn't be looking at only the traditional control systems, but you'll be also having a huge area to look at in the cyber security as well. And then finally, you'll be looking at in the outlook or the future, there'll be more concerns about reducing the carbon footprint and sustainability as well. So especially in this current world, that we have a lot of issues with global warming and things. So the new systems, for it to be even more efficient and things, it will tend to have a look at those ones as well, so that as you are producing and the maximizing profit, you're not also releasing so much poisonous gases or flue gas into the system or into the environment. All right, I think I will end here with the future outlook, and thank you very much. If there is any question, I think you can ask or anything. Thank you very much.
Well, thank you so much, Engineer James, for that educative, insightful presentation. And you were also very time conscious. We really appreciate that. So now, guys, the floor is set. If you have any questions, you can raise your hand or put it in the chat box and it will be read out to him. Okay, so I think I'll go first. Engineer James, during your presentation, you made mention of the process control. You made mention of the commonly used instrumentations, that is the orifice plates, and also the control technologies like PLC, DCS. I want to know the link between them. So let's say you have an orifice plate where it's like you are flowing through that. So with the control technologies, is it something that is within, or it's an external part that controls it, that controls the orifice, whatever is the variable going through the orifice plates?
Okay. All
I
right.
mean,
So yes, with that, for instance, like the orifice plate meter, it is just measuring the flow rate in that sense, and then it is linked what the reading that is being read on the meter, the orifice plate, that is being sent by electronically to a junction box, and then it goes into an equipment room where you have the servers and things. So that is where you have the DCS, or you have the PLC, or you have the SCADA system. So the system is like installed on the PC, on the server, and then you have links from there to the transmitter in the field. So the field um, transmitter reads that and then sends it electronically to the controller, which is in this case the DCS. And then it will show it in the operator station for the operator to see what's happening. And he sees that maybe the flow is going so high, so I want to reduce it. And then he will input some actions on and then based on that, the controller will send it, in this case, the DCS will send it back to the field equipment. If it's the final element is a valve in that case, to start to reduce it or to close it in that sense. I don't know if you are clear on it.
Yeah, I get it now. Thank you so
Yes.
much. Okay, Kelvin, you can unmute and ask your question.
Hi, thank you so much, Engineer, for the presentation. And so I do a bit of instrumentation, and now I realize that some of the new equipment out there, if you have to do like a diagnosis or verification, you just you just take a laptop, you connect directly via USB, and then you're able to do a verification, and the equipment gives you the errors and all of those things. So I'm now looking at the instrumentation role going into the future, and then I want to know what does that look like as an instrumentation engineer going into the future. So now there's a lot of Internet of Things, and you have to know something digital. Like, what's the outlook in the future for the instrumentation role?
If I get you clearly, I mean the current one, the base transmitters or instrumentation that we have, for instance, and then now the new ones like the smart ones where it those ones will have to they can do some diagnosis on themselves to show you that this is about giving a fault based on the readings and the recordings. So it can tell you that okay, this this transmitter is developing some fault, and then you need to change it or you need to work on it or that sense. I don't know if it clarifies, or maybe you can clarify the question well.
Yes, so I'm saying that now that the transmitter sort of does its own diagnostics and gives you what to do, it's like now one person can do a lot of different tasks. So as an instrumentation engineer, like for the future, what sort of skills are we looking at now? Do you have to be a digital person, or like the traditional instrumentation role, how is it changing?
Well, I believe you have the same the basics of instrumentation will be the same, but you have to upgrade yourself with the uh, a bit of more digital stuffs. Um, even the programming areas when if you want to move into the DCS and stuff, because it will be evolving into new areas where just the job that you may be doing now, you may not have to do them because the transmitter is showing you everything. But just that you still have to get the knowledge. For instance, if you have to do a calibration on a pressure transmitter, you have to get a, a known pressure reading or something. You have to, and then you compare with it and see that if the transmitter is working properly, or the reading that is giving you is consistent with it. I think these ones will not change, but it's just the diagnosis and things that you may not have to, maybe to reduce the preventive maintenance. For instance, if you have to do take every transmitter out and then go and check if it is working properly. Maybe you have about 500 transmitters in the plant. You have to, every month you have to schedule and then go to each and every one of them and then remove and take it to the lab and then check and test it and then fix it back and all those things. So some of those jobs will be limited in the sense that the transmitter will be showing you all those things. But when it comes to the work itself, the instrument engineer will have to still do that.
Okay, Kelvin, does that answer your question? Okay, all
Yes.
right. So Paul, all right, thank you. Paul, you can unmute and talk now.
Okay, thank you very much, Engineer James, for such a presentation. Please, I have two questions, and my first question goes, you mentioned that the three standard controller modes That's manual, automatic, and then the cascade one. Please, I would like you to throw more light on the cascade one, if possible. And my second question to you mentioned the PID, that's the proportional, integral, and then derivative. If you can also throw more light on how the integral works. Thank you.
Okay. Okay, so the first one is the mode of operation, the manual and the automatic and the cascade. Now, the cascade is where you have one controller that is controlling another one. For instance, let's say you have a cooler that you want to use the cooler to, like cooling fans, for instance, to drop the temperature of a process. Now you have a temperature indicator controller that will measure the temperature of the process, and then it will put the target or the set point in the controller. Let's say you want to keep it at 50 degrees, for instance. So that is one controller. And then there's another controller for the speed of the cooler. So the output of the first controller, which is the master, will be the set point of the slave controller, the new one, the smaller one that you are bringing in. Yeah, it's usually termed as a slave controller. So that one will be that of the set point for the slave one, and then per the output that is coming from the master controller, then to tell the speed to either increase or reduce in that sense. So that is how the cascade is. It can be applied in a lot of other areas as well. And then the PID controller, the integral part is for it's basically for accuracy of the as the proportional one is just on off control. The integral one is for it tries to for instance, when the proportional comes in, there's a little offset. It's not able to give exact accuracy. It's not able to bring it back exactly as it is. And there's a little offset from the target. So the integral part is good for clearing off that offset. So it's just a little above or below that set point. And the integral is able to ensure that you bring it back to that's the set point. There are systems which that minor offset is not a big problem. So in that case, you can just use the proportional. But others which you need that accuracy. So the integral part will be doing that function. Once the proportional part has taken action for the bigger correction, and then that little offset that happens, then the integral part, which is for the accuracy, will try to resolve that and bring it back to the target or to the set point. I don't know if it clarifies your question.
Yes, please. But so please, if I'm getting you right, so let's use a flow valve for an example.
Okay.
If you have a flow valve and then you want it to open at maybe 15 degrees percent. No, sorry. You want to open the valve by 15%. And then maybe by one or two errors from the system, it's open 15.9, 15.8. Is it the integral that will bring it back to the 15% opening?
Yes. So there's the integral is the one that will remove that little offset. Usually the control valve, for instance, it doesn't take, for instance, if depends on the disturbance that will come in the system, and it will either open or close. But it doesn't go straight to the set point. For instance, you want it to open at 15% like you said. Initially it was around 4%, and now there's a disturbance in the system and it has to open to 15%. It will not move straight from 4 to 6 because it will just use by the proportional part, it will just try to offset that error, and then it can shoot it up to maybe around 17, and then it will recalculate and then drop it back to around maybe 13, and then recalculate, drop it back, increase it to 16, and then it's like a sinusoidal thing until you achieve the target. So it doesn't go straight to it. So the integral part is what will be doing that little calculation for the small offset above or below the set point to bring it back to it. So like you said, if 15 is reading now 17 now, start to recalculate and to bring it back to the 15. That sense, yeah.
Thank you very much, sir.
All right, you're welcome.
Okay. I'm concerned, Evans, you had your hand up. Do you still want to proceed with your question? Or yeah, okay.
Thank you very much for this presentation. Please, my question was answered, but I just wanted to add this one up too. I don't know whether it's a question or a suggestion. Please, with the feature trend, which is you said feature trend, which is the smart sensors, IoT, and the machine learning. Are there anything being done as we are talking right now? Like, is there any research being done on it? Because recently I did my project, final year project on this pressure sensor monitoring system, of which my focus was not on the three listed control technologies, that's the PLC and then DCS or the SCADA, but mine was MATLAB. Hello, please, can you hear me?
Yes, you're loud.
Yes, I can.
Oh, okay. Mine was on MATLAB, and though we didn't get to do a prototype of how it will look like, but we're able to do some simulation. We're able to do some simulation, and also integrated this AI and the machine learning tools, of which we're able to monitor a system by, let's say, when there's a threshold, the system automatically cuts off, and then, but when it's below it gives a signal. And that's why I asked if there's any current research being done in where you are working. Yes, I'm done.
Okay. So the current or the older industries doesn't have this new, but they are existing. There are things that have started, and they are maybe new ones. New industries have that. Maybe just the cost and things that you will have to consider, because all these things are considered to choose a particular system or something. So they are done to choose a specific system. So they are existing, although, but it might not be per the course and the fault, resolving the fault and things. You have to look at all these things, because during the engineering phase, you consider all these things before you use a particular system. So even though there are existing ones which have this smart sensor being applied and things, before you get a particular system into your plant, you don't just look at the fact that this one functions this way or that, but you look at how it can communicate with other systems and things and the cost involved. Maybe because it's a newer system, and then it can give you the smart features and things. But what you need is just to read a little temperature or something. It's not so critical to you. In that sense, you wouldn't want to spend maybe thousands of dollars to buy this when you can buy maybe some $50 or $100 thing, which can do the same thing. So all those things come, but there are existing ones which have these features. It's not like a new one. Just that in the future, newer plants will be incorporating more of it into the system. But even now, they are existing. Yes.
Okay, thank you, sir.
You're welcome.
Thank you so much, Engineer Asma, for that comprehensive presentation and answering of our questions. We really do appreciate the efforts that you have given to today's session. God richly bless you.
Thank
Hello.
you.
We would be sending a link into the chat box. Kindly tap on that link and give us a feedback on the session so far. So we'll be looking out in the chat space for the link. Also, look out for our upcoming events in November, and that one is dubbed the Safety Month. We are going to have a lecture series on occupational health and safety and risk management systems in the industry. So kindly follow SPE on LinkedIn, on X, and on Instagram. We'll be sharing the flyer as soon as they are readily available. Okay, to crown it all, we would invite Isabella Donko, the Student Liaison Committee Chair, to give us a vote of thanks. Isabella, if you're on the call, kindly unmute and proceed. Okay, looks like Isabella is missing in action. All right, so first of all, great thanks goes to the Almighty God for giving us the opportunity to organize such a lecture series. We owe it all to him. And to our speakers, especially today's speaker, Engineer James Asma, for that insightful and educative and comprehensive lecture that you have given us. We really do appreciate it. And we say, Ayiko, thank you so much for all of it.
You're welcome.
So guys, I think this is the end of the lecture series. My name is Harrison Amwa and I was your moderator for today's session. You can connect me on LinkedIn and we'll take it from there. See you same time next month. Bye.
Bye.
Bye. Thank you very much.